Here, we'll work out some examples of finding general solutions to and sketching phase portraits for constant coefficient linear systems of differential equations with two components. We've got three examples here that I want to try to analyze and see what their solutions look like and what their phase portraits look like. So let's start with number one. For this one, we have the matrix 5 minus 2, 5 minus 1. And we can start by finding the eigenvalues and eigenvectors for this matrix. So for this, A minus lambda I is given by 5 minus lambda minus 2, 5 minus 1 minus lambda. And so the determinant, or giving the characteristic polynomial of this matrix, is 5 minus lambda, negative 1 minus lambda, plus 10. This is lambda squared plus 1 minus 5 is minus 4 lambda. And I have minus 5 plus 10 is plus 5. This doesn't factor, but the quadratic formula will give me that lambda should equal 4 plus or minus the square root of 16 minus 20 over 2 is 2 plus or minus I. Number one here is the complex case. So I have to find one of the eigenvectors from one of these eigenvalues. I will take the 2 plus I version. So for lambda equals 2 plus I, the matrix A minus lambda I looks like 5 minus 2 plus I, or 3 minus I, negative 2, 5, negative 1 minus 2 plus I is minus 3 minus I. To see that things cancel here, I'll multiply the first row by 3 plus I, because that'll determine the top left become a real number. So if I do that, this becomes 3 minus I times 3 plus I is 9 plus 1, or 10. We have negative 6 minus 2I, 5 minus 3 minus I. And we can see here that these two rows are identical, ought to be multiplied by 2. And so to find an eigenvector, I can use the fact that based on the bottom row here, 5v1 minus 3 plus I v2 equals 0. Now, one way to do this is by picking v1 equal to 3 plus I and v2 equal to 5. If I do that, this expression becomes 0. So I can choose that for my corresponding eigenvector. So what I get here is my eigenvalue is 2 plus I. My eigenvector is 3 plus I and 5. So therefore, my complex solution will look like the following. X of t is e to the 2 plus I t times 3 plus I and 5. I can decompose this Euler's formula into e to the 2t cosine of t plus I sine of t, and then times 3 plus I and 5. And I can now distribute this into the vector, giving me 3 cosine of t plus 3I sine of t plus I cosine of t minus sine of t, because the 2i's give me minus 1. 5 cosine of t plus 5I sine of t. And then I can group the parts that do have an I from the parts that don't to give me e to the 2t. The ones that don't have I is a 3 cosine of t minus sine of t, and a 5 cosine of t on the bottom, plus the part that do have an I, still the e to the 2t, 3 sine of t plus cosine of t, and a 5 sine of t on the bottom, which means that my general solution here is C1, the real part, plus C2, the imaginary part, which looks like this. You can leave the e to the 2t outside the vector or put it inside. Both versions are okay. But now I want to sketch the phase portrait. And to do that, I want to plot one of these functions, and then I'll tell you how everything has to rotate. Now I know from my setup I'm going to have a spiral source, because it's e to the 2t, it's a positive value. And so my phase portrait should represent that. So if I start with the first part of the solution, the C1 term, I look at t equals 0, and I plug that in, I will be at the point 3, 5, because cosine's 1 and sine is 0. So 3, 5 puts me somewhere up here. I go up a little bit to, say, pi over 2, which is the first time cosine goes to 0, I'll be at negative 1, 0. Negative 1, 0 is on the x-axis to the left side of the origin, but this is a spiral source, so it won't be at negative 1, 0, it'll be at something bigger than negative 1, 0, because we're spiraling away. It'll be somewhere over here. and that will indicate that we're spiraling in this direction as a spiral source. So going backwards would come in something like this. And if we were to draw this second one over here, I would get a similar picture where I would start at 1, 0 and end up at 3, 5. So it's going this way. So we do get our spiral source, and that's the direction of rotation we get by plotting these different solutions. Now, problem 2. Problem 2 had the matrix 4, -1, 1, 2. So determinant of A minus lambda I is given by 4 minus lambda, 2 minus lambda, plus 1, lambda squared, minus 2 minus 4 is minus 6 lambda, 8 plus 1 is plus 9, which is lambda minus 3 squared. This is my repeated root case here. So for lambda equals 3, A minus lambda I becomes 1 minus 1, 1 minus 1. Great. These rows are definitely the same. And so we can pick as an eigenvector here 1, 1, because 1 plus minus 1 is 0. Now, because we're in the repeated root case, we only got one eigenvector, we need to do the generalized eigenvector thing to find a second one. And so W is defined by A minus lambda I W equals V, or with the equations we have here, 1 minus 1, 1 minus 1 W equals 1, 1. If we put in a vector W1, W2 for W and work this out, this will tell us that W1 minus W2 should equal 1, and that's what both equations tell us. So we can pick anything to make this work. So I will pick W1 equals 1 and W2 equals 0. Anything else you pick here is totally fine, provided it satisfies that equation. So with this choice of W and our V right here, our general solution is going to be x of t is C1 eigenvector 1, 1 e to the 3t plus C2 eigenvector t e to the 3t plus our generalized eigenvector e to the 3t. Now, because these are e to the 3t, it's all positive numbers, this will be an improper nodal source. And so our phase portrait should show that. For the phase portrait, we first want to draw in our eigenvector and our straight line solution, which is our C1 term here. It's 1, 1 e to the 3t. So along the 1, 1 direction, going away. And now to get the right curvature here, I need to figure out what this second term looks like. Well, if I collapse it all together, I will see a t plus 1 and t e to the 3t. So at t equals 0, this is at 1, 0. So it's over here. And as t goes to infinity, this winds up in the first quadrant because both terms are always positive as t goes to infinity. And so this will end up approaching this way as time goes on. And so backwards, it loops through this way. You also tell that for t between -1 and 0, we're in quadrant 4. And with t less than -1, we're in quadrant 3. The curve on this side will mirror it, so it'll go this way and this way, and so that is our phase portrait for this system as an improper nodal source. Finally, we have example 3. Matrix A was 3 minus 3, 2 minus 4. So determinant of A minus lambda I is given by 3 minus lambda minus 4 minus lambda plus 6. So lambda squared, I have plus 4 minus 3, so plus lambda, plus 6 minus 12 is minus 6, and this factors as lambda plus 3, lambda minus 2. So our two eigenvalues here are 2 and minus 3. For lambda equals 2, A minus lambda I becomes 1 minus 3, 2 minus 6. Those are the same up to doubling the first row to match the second row. So therefore, we have that v1 minus 3, v2 must be 0, or we can pick an eigenvector of 3, 1 for this one. For lambda equals minus 3, A minus lambda I is 6 minus 3, 2 minus 1. The bottom row is now 1/3 the first row, so they're repetitive and redundant. So we know that 2v1 minus v2 must be 0, or I can pick an eigenvector of 1, 2. So therefore, my general solution will be x of t is c1. Our first eigenvalue was 2. The eigenvector is 3, 1. So c1, 3, 1, e to the 2t plus c2, 1, 2, e to the minus 3t. Because we have two eigenvalues of different signs, this will be a saddle. And so our phase portrait should show that. Going outward is the direction 3, 1 with the e to the 2t eigenvalue. So it goes this way out. And 1, 2 is coming in with the e to the minus 3t. Therefore, our saddle will follow these two straight lines, doing something like this each of the 4 respective regions here. So there's 3 examples of how you find general solutions and then sketch phase portraits for complex, repeated, and real and distinct eigenvalue problems when you have a constant coefficient linear system differential equation you're trying to solve with the eigenvalue method.